Shut-in procedures. Introduction. Shut-in procedure should be agreed by contractor and operating company and posted on rig floor before drilling the well begins. When any positive indication of a kick is observed, such as a sudden increase in flow or an increase in pit level, then the well should be shut in immediately without doing a flow check. If the increase in flow or pit gain is hard to detect, then a flow check can be done to confirm the well is flowing. If surface hole is being drilled and the conductor pipe is not set in a competent formation and a shallow gas kick is taken, then the gas should be diverted. This will be discussed at the end of this section. The procedures which follow are generally suggestions and not necessarily applicable to any specific rig. Soft shut-in procedure while drilling. 1. When any indications are observed, while drilling, that the well may be flowing, stop rotating the drill string, raise the drill string with pumps on until tool joint is above the drill floor. 2. Stop pumps and check for flow, if positive. 3. Open choke line HCR valve. 4. Close BOP. 5. Close choke. If the choke is not a positive closing choke, then close a valve downstream of choke. 6. Call supervisors and commence plotting a graph of shut-in drill pipe pressure. Check pit volume gain. 7. Refer to APIRP 59 Section 3.8 for the advantages and disadvantages of the soft shut-in. Note: choke in open position while drilling. Soft shut-in procedure while tripping. 1. If there is an indication of swabbing and the well flows during a flow check, proceed as follows. 2. Set the slips. 3. Install full opening safety valve, Kelly cock. 4. Close safety valve. 5. Open choke line HCR valves. 6. Close BOP. 7. Close choke. 8. Call supervisor and check pressures. 9. Install inside blowout preventer, gray valve or non-return valve. 10. Open safety valve. 11. Reduce annular preventer pressure and start stripping drill pipe in the hole. Note: choke in open position while tripping. With a swabbed kick there are 4 options. 1. Strip back in hole. 2. Perform a volume trick bleed. 3. Bullhead kick back into formation. 4. Perform off bottom kill, then return to bottom and circulate well to desired mud weight. Hard shut-in procedure while drilling. 1. When any indication is observed while drilling that the well may be flowing, stop rotating the drill string, raise the drill string with pumps on until tool joint is above the drill floor. 2. Stop pumps and check for flow, if positive. 3. Close annular or pipe rams. 4. Open choke line HCR valve. 5. Call supervisor and commence plotting a graph of shut-in drill pipe pressure. Check pit volume gain. 6. Refer to APIRP 59 sections 3:7 for advantages and disadvantages of the hard shut-in. After the well has been shut in. In any shut-in procedure it is prudent to line up the annulus to the trip tank above the annular or rams. This will assist in double checking to see if they are leaking. Double check that the well is lined up through the choke manifold prior to circulating kick out. Fast shut-in procedure while drilling. 1. When any indication is observed while drilling that the well may be flowing, stop rotating the drill string, raise the drill string with pumps on until tool joint is above the drill floor. 2. Stop pumps and check for flow, if positive. 3. Open choke line HCR valve. 4. Close annular. 5. Call supervisors and commence plotting a graph of shut-in drill pipe pressure. Check pit volume gain. Note: there are no A.P.I recommendations for the fast shut-in. Diverter procedure while drilling. When drilling top hole, a diverter should be installed, and it is good practice to leave the diverter installed until 13 3/8 casing has been run. An automatic diverter system should first: A. Open an alternative flow path to overboard lines. B. Close shaker valve and trip tank valve. C. Close diverter annular around drill pipe. D. If there are 2 overboard lines, then the upwind valve should be manually closed. While drilling top hole. If any indication of flow is observed while drilling top hole, close diverter immediately, as the gas will reach surface in a very short time and it is inadvisable to attempt a flow check. Suggested diverting procedure in the event of a shallow gas kick. A. Maintain maximum pump rate and commence pumping kill mud if available. B. Space out so that the lower safety valve is above the drill floor. C. With diverter line open close shaker valve and diverter packer. D. Shut down all non-essential equipment. If there is an indication of gas on rig floor or cellar area, then activate deluge systems. E. On jackup and platform rigs, monitor C for evidence of gas breaking out around conductor. F. If mud reserves run out, then continue pumping with sea water. G. While drilling, top hole afloat should be run. This will prevent gas entering drill string if a kick is taken while making a connection. It will also stop backflow through the drill string on connections. Surface and subsea bops while wireline logging. Direct the wireline loggers to cease operations and close the well on the upper annular. Open kill line valves and begin to record shut-in pressure and pit gain. Password to the oil company representative and senior drilling contractor representative of the well condition. Decide on kill program. Note, if at all possible, the wire line should be pulled or stripped out of the hole. If the line needs to be cut and dropped, a surface hydraulic cable cutter should be used. The shear rams should be considered as a last resort and used only if the annular S fail to secure the well. Closing in kicks. Soft close-in procedure. For a soft close-in, a choke is left open at all times other than during a well control operation. The choke line valves are aligned such that a flow path is open through the choking system, with the exception of one choke line valve located near the blowout preventer. When the soft close-in procedure is selected for closing in a well, the 1. Choke line valve is opened. 2. Blowout preventer is closed, and 3. Choke is closed. This procedure allows the choke to be closed in such a manner to permit sensitive control and monitoring of casing pressure buildup during closure. This is especially important if formation fracturing and broaching to the surface is likely to occur if the well is closed in without regard to the possibility of excessive initial closed-in casing pressure. Hard close-in procedure. For a hard close-in, the chokes remain closed at all times other than during a well control operation. The choke line valves are aligned such that a flow path is open through the choking system with the exception of the choke S itself and one choke line valve located near the blowout preventer stack. When the hard close-in procedure is selected for closing in a well, the blowout preventer is closed. If the casing pressure cannot be measured at the wellhead, the choke line valve is opened with the choke or adjacent high pressure valve remaining closed so that pressure can be measured at the choke manifold. This procedure allows the well to be closed in the shortest possible time, thereby minimizing the amount of additional influx of kicking fluid to enter the well bore. Use of the hard close-in procedure is limited to well conditions in which the maximum allowable casing pressure is greater than the anticipated initial close-in pressure and a well fracture would not be expected to broach to the surface on initial closure. Soft close-in versus hard close-in procedure. The soft close-in procedure provides a means of monitoring casing pressure and a more sensitive control of casing pressure buildup during closure than will be experienced using the hard close-in procedure. If the initial closed-in casing pressure is likely to exceed the maximum allowable casing pressure, the soft close-in procedure permits initiation of a low choke pressure procedure or other alternate procedures before maximum allowable casing pressure is reached. In this situation, the soft close-in procedure has a distinct advantage over the hard close-in procedure. The major disadvantage of the soft close-in procedure is that the additional time involved in opening the choke line valve and closing the choke will allow additional influx into the well bore. This procedure will result in a larger kick volume and potentially higher casing pressure than obtained if the hard close-in procedure is used while circulating out the kick. The hard close-in procedure is somewhat less complicated, can be performed by one man working on the rig floor, and is more likely to be performed without inadvertent delays in closure than the soft close-in procedure. Stabilized pressures. When a kick is detected, the well should be closed in as quickly as possible to minimize kick influx volume. The figure shows a schematic diagram of a well shut in on a kick. In this well, a 20-barrel gas influx occurs when drilling at 10,000 feet with a 10.0 IB/gal drilling fluid. The stabilized closed-in pressures are 500 psi on the drill pipe and 640 psi on the casing or annulus gauge. Pressures in well bore. The figure illustrates various pressures in the well bore. To understand how the various pressures interact, it is necessary to isolate and identify each one. The drill pipe gauge pressure plus the hydrostatic pressure of the drilling fluid equals the formation pressure. The same pressure balance can be made for the annulus, i.e., casing gauge pressure plus the hydrostatic pressure of the annulus drilling fluid plus the hydrostatic pressure of the influx equals the formation pressure. Gas migration. The figure illustrates an example of a 10,000-foot closed-in well with 10.0 IB/gal drilling fluid and a small volume of gas at bottom. When the gas rises to 5,000 feet without expansion or temperature change, the bottom hole pressure rises to 7,800 psi, which is equivalent to a 15.0 IB/gal drilling fluid column. When the gas reaches the surface, bottom hole pressure is 10,400 psi, which is equivalent to a 20.0 IB/gal drilling fluid column. At 5,000 feet the borehole pressure is equivalent to a 30.0 IB/gal drilling fluid column to that depth. Such excessive pressure should be avoided whether gas rises through a static drilling fluid column or is circulated out by allowing the gas to expand as it rises. This also requires that the pits be allowed to gain volume. If a gas bubble is permitted to rise in a wellbore without expanding, the gas pressure will remain constant. The reduced hydrostatic head above the gas column must be overcome by increased surface pressure on the casing. In turn, this increased pressure results in a higher bottom hole pressure. Closed-in drill pipe pressure. Formation pressure near the wellbore is reduced during flow. When the well is closed in, the borehole pressure will rise until equal to formation pressure. As the drill pipe, an annulus, is in communication, the drill pipe pressure will also rise and stabilize. The drill pipe pressure at this time indicates the amount to increase the drilling fluid density. If the well is not circulated, the gas will slowly rise and increase both wellbore and drill pipe pressures. Drill pipe pressures read after the initial stabilized reading will indicate excessive drilling fluid density increase. To avoid excess wellbore pressures, the choke should be used to bleed drilling fluid from the casing and maintain the initial shut-in drill pipe pressure. To determine the closed-in drill pipe pressure when a back pressure valve is in the drill string, pressure should be increased slowly using the smallest pump available to determine the pressure at which the back pressure valve opens. If casing pressure is seen to rise while pumping on the drill pipe, pumping should be stopped and the increase in casing pressure subtracted from drill pipe pressure. Formation integrity tests. Leak-off test. A leak-off test is made to determine the pressure at which a formation will begin to fracture. Leak-off tests are usually run after drilling a short distance below the surface casing shoe. These tests may also be made on other casing strings. A leak-off test is performed by pumping drilling fluid into the wellbore at a slow rate, typically 1/2 barrel per minute, with blowout preventers closed and carefully plotting the resulting pressure versus the total volume pumped. The pressure at which the plotted curve begins to flatten, i.e., when the pressure increases a smaller amount for a volume pumped, is the surface leak-off pressure. The pump should be stopped immediately. This pressure plus the hydrostatic pressure of the drilling fluid is the formation fracture pressure. Formation integrity tests. Leak-off test. Formation fracture pressure, psi, equals. It is useful to calculate the formation fracture gradient as equivalent or fracture drilling fluid density. Fracture drilling fluid density, IB/gal, equals. Fracture pressure is the maximum surface pressure that can be applied to a casing that is full of drilling fluid without fracturing the formation. Fracture pressure is calculated as follows. Formation competency test. A formation competency test is made to determine if a wellbore will support drilling fluid of a higher density which may be required at some future time during the well drilling and completion operations. The formation competency test is performed by pumping drilling fluid into the wellbore at a slow rate, typically 1/2 barrel per minute, with blowout preventers closed. Pumping into the wellbore should be continued until reaching the predetermined test pressure as calculated below.